Okay, for this problem, we're doing number 2 from the review problems. So we have another kind of race of the shapes question. So we have a solid sphere of radius r is placed at a height of 30 centimeters on a 15-degree slope. It is released and rolls without slipping to the bottom. From what height should a circular hoop of radius r be released on the same slope in order to equal the sphere's speed at the bottom? So it looks like we're looking at, okay, we have a sphere, and if you remember from class, the sphere won the race every time. So we're going to find the velocity for the sphere, and then what we're going to do is we're going to use that to find a different height that we can release the hoop from, a higher height, to see what that height would be to achieve the same speed as the sphere. So we'll do our givens and finds. So we have given, so we have y initial for the sphere is equal to 30 centimeters. Theta is equal to 15 degrees for the slope. We have a radius r, and then we need to find, well, I have a couple more givens actually that we just have to know because we're talking about a sphere and a hoop. So we want to know I for the sphere that's equal to 2/5 mr squared, and I for the hoop is equal to mr squared. And we're going to find the initial height, yi, for the hoop. All right, so this is our figure. This is before and after. And this is an energy problem, so we're going to be using energy. So EI is equal to EF. And if we just do a quick energy bar chart, we're just going to do a before and an after. So before, we have all potential energy and no kinetic energy. So we have U initial, and then we have nothing for K initial translational or K initial rotational. So I'm just going to say K is my translational like we've always used, and then I'm adding this R to show that it's rotational. And so this is like before. And then after we've lost there's no U final, so we have no gravitational potential energy because it's at the bottom of the hill. But we have K final and K final rotational. So we're going to have some combination of them. Say something like this. We're not exactly sure, but that's what we would expect. And so this helps us, these energy charts helps us to fill in our energy equation. So I'm going to have Ui plus Ki plus Kir rotational is equal to U final plus K final plus K final R. Okay, and so we know we have no kinetic, translational, or rotational, so those are going to go to 0. It's not moving at the start. And then at the bottom we know we have no potential. So I'm going to have mg y initial for the sphere is equal to 1/2 mv squared final for the sphere plus 1/2 I omega final for the sphere squared. Okay, so because we have two objects that have different moments of inertia, I don't want to have to do the equation twice. Continue on with the equation twice. What I'm going to do is I'm going to represent the coefficient in front of mr squared, this, and then this is 1. I'm going to represent these by k. So for now I'm going to have I is equal to k mr squared. And when we get to the specifics of whether it's the sphere or the hoop, then we'll plug in what k is. So mg y sphere is equal to 1/2 v final squared plus 1/2 k mr squared times omega final squared. Okay, so and I'm just going to get rid of the sphere here. So it can be either, we can be talking about either one. So now we know that when we're rolling without friction that V is equal to omega times R. And so I want to substitute in for omega. So I want to use omega is equal to V over R and plug that in here. So I'm going to have mg y initial is equal to 1/2, oops, I forgot my m, v final squared plus 1/2 k mr squared, and then I'm going to plug in v squared over r squared. So I can cancel out my r squareds, and I can cancel out through with my m's and get rid of my m's. So I have g y initial is equal to 1/2 v final squared plus 1/2 k v final squared. So I want to get v final squared alone, so v final squared. So there's 1/2 here, so I can pull out the 1/2. So it's before we switch sides. G y initial is equal to 1/2 v final squared. And I'm left here just with a 1 when I factor that out, plus k. So I'm searching for my v final. I want to know what my v final is for the sphere. So I'm going to multiply both sides by 2 and divide both sides by 1 plus k. So v final squared is equal to 2gy initial over 1 plus k. And then I know that's a square root, so I'm going to take the square root. Okay, so that's my velocity. And now to say that it's for the sphere, velocity final for the sphere is equal to 2gy initial for the sphere over, now for the sphere it's going to be 1 plus 2/5. And so we can rewrite that as 2, and this is square root 2gy initial s over, and now so I have 1 plus 2/5 is equal to, I'm going to turn the 1 into a fraction, so I'm going to call this 5/5. That's my equal to 1 plus 2/5. So I get this is equal to 7/5. So this is going to equal 7/5 square root. And so that's equal to, so 2 over 7/5 is equal to 2 times 5 over 7. So I get 10/7. So 10 over 7 gy of the sphere. So that's its velocity. I'm not going to plug in yet because you'll see when we get to the hoop, we're looking for my yi here, and we need a new yi. So I'm going to go back to this equation, and actually I want to write this out further and say this is yi is equal to v final squared over 2g and 1 plus k. So I need that as an equation that I've been using, and then this is the equation that I was using. Okay, so I need this equation, this for the hoop. So for the hoop, so now that I know the velocity, I know the equation for velocity for the sphere, let's see if I can plug that in and figure out the new height for the hoop. So yi for the hoop is equal to v final squared of the sphere divided by 2g. And now I'm going to plug in the k for the hoop, 1 plus 1. So that's equal to v final squared of the sphere. And now there's a 2 here and a 2 here, right? So 2g and then times 2. So I can cancel out the 2's, and I have v final squared of the sphere over g. So if I plug in this v final squared for the sphere, I get, so since this is squared, I just get what's inside, 10 over 7 g initial for the sphere over g. So my g's cancel. Y initial hoop is equal to 10/7 y initial to the sphere. So now I can just plug in, and so that's equal to 10 over 7 times 0.3 meters, or y initial for the hoop is equal to 0.43 meters. So we were able to do that without actually plugging in numbers to find this number, and just look at and find out by leaving our terms and variables, we were able to see how y for the hoop is a function of y for the sphere.